That one was too easy, right? Welcome back. This is the third part talking about the heart. And so we're going to talk about the cardiac cycle. And so the cardiac cycle is just one heartbeat. So complete sequence of events in the heart during one complete heartbeat. So it includes what's called atrial systole and then diastole, followed by ventricular systole and diastole. And so we're just going to talk about blood flow, and I just want you to keep in mind that blood does not know where we want it to go. It's only going to be based on pressure. So let's go ahead and watch it before we discuss it.
The heart is a pump which must circulate blood through two different but interconnected vascular systems. The smaller of these systems is the pulmonary system. Blood returning from the upper part of the body is delivered to the right atrium of the heart by the superior vena cava, one of the body's two largest veins, while blood returning from the lower part of the body is delivered to the right atrium by the other major vein, the inferior vena cava. Contraction of the right atrium in each cardiac cycle forces blood into the right ventricle. This is followed by contraction of the right ventricle, which pumps blood into the pulmonary artery, sending it on through the blood vessels of the lungs. As the right ventricle contracts and pressure within the right ventricle rises, the tricuspid valve situated at the opening between the right atrium and right ventricle shuts, preventing any backflow. The pressure generated by contraction of the right ventricle soon opens the pulmonary valve and blood enters the circulation of the lungs. After passing through the circulation of the lungs, the blood, having been recharged with oxygen and having rid itself of carbon dioxide, is returned through the pulmonary veins to the left atrium. The left atrium, too, contracts, forwarding blood into the left ventricle in order to fill it before it contracts. As the powerful left ventricle contracts, the mitral valve shuts, preventing backflow into the left atrium. The aortic valve opens and blood is forced into the aorta, which distributes it to the rest of the body apart from the lungs. As the contraction comes to an end and pressure in the aorta falls, the aortic valve snaps shut to prevent backflow into the left ventricle.
Okay, so before we run through this process, there's 5 things I want you to remember and keep in mind. Number 1 is that blood flow follows pressure gradients. So it's going to flow from a high pressure to a low pressure. The next thing is that increased blood volume is going to increase blood pressure. And so think of these ventricles, they're going to be confined spaces if you close the valves. And so the more blood in that space is going to increase that pressure. Systole is the word for contraction. So when the ventricles or the atria, those muscles in the myocardium, contract and are ejecting blood. So systole is the ejection phase. Diastole, this word means relaxation. And so this is when the chambers will be filling. They fill during diastole. So they're going to eject blood during systole. They will fill during diastole. The atria, so those upper chambers, and the ventricles, the lower chambers, are going to alternate systole. So they're never going to contract at the same time. Because think about it, top chambers contract and bottom chambers contract. They're working against each other, so that doesn't make any sense. Atrial contraction is going to be before ventricular contraction. And of course, valves are going to close to prevent the backflow of blood. And so we're going to walk through one cardiac cycle. And I'm never going to say what happens in phase 1, what happens in phase 2, that sort of thing. I'm more concerned that you understand how it happens and then the sequence. So I would give you some sort of context. This is because some textbooks divide it up a little bit differently, and I'm not really going to get hung up on that. But I'm going to just give you this picture. And so we're going to start, one cardiac cycle begins right after that second heart sounds. So you hear lub-dub, and then that begins the next cardiac cycle. So we're going to start off with ventricular filling, because to be quite honest, we care more about the ventricles than the atria, because the ventricles are what are actually ejecting the blood out of the heart. So during phase 1 of ventricular filling, the atria and the ventricles are both in diastole. And so they are in diastole, so they are relaxing. And what I'm going to tell you is that the aortic and the pulmonary valves are going to be closed. The heart is at rest, and blood is going to passively flow through the atria into the ventricles. They're going to passively fill about 80% of the way, and that's good. Like I said, your heart has to beat your whole life. The heart needs a rest. That's the only time it's actually getting blood delivered to the cardiac muscle cells so they can take that oxygen and nutrients and make ATP. The atria, which are very small and thin-walled, will then contract, and so that's called atrial systole. Their job really is just to top off the volume in these ventricles. At the end of the rest, so ventricular rest, the amount of blood inside the ventricles is called end diastolic volume. And so that's approximately 130 mils in each of the ventricles. When the ventricles contract, so now we're beginning ventricular systole, the atria are going to be relaxed. So remember, they never contract at the same time. So the beginning of ventricular systole, those atrioventricular valves are going to slam shut. So AV valves close at the beginning of phase 2 ventricular systole. So kind of pop up here. So we had the atrioventricular valves were open. We had filling of the ventricles. The atria contracted and topped off that volume. So we have about 130 mils, so end diastolic volume. When the ventricles contract at this moment, both the atrioventricular valves and the semilunar valves are closed. And that's what this little 2A is showing you. Since the walls are contracting, we are building up pressure inside the ventricles. And so just imagine if you glue up a balloon with air and you tied a knot in it and then you squeezed it. You would be increasing the pressure inside of the balloon. Same kind of idea. And so don't forget that first heart sound, that is going to be that lub, so the atrioventricular valves closing. So hold on a click. So the next phase is going to be ventricular ejection phase. The pressure is going to get so great, it has to be greater than the pressure in the vessels. And so we have the atria relax, the ventricles contract, those papillary muscles contract, pull in the chordae tendineae to prevent AV valve prolapse. So now we have enough pressure in those semilunar valves, so the pulmonary valve and the aortic valve, like our saloon doors, they're going to fly open and the blood is going to be ejected. So ventricular ejection phase. What leaves the heart per beat, so amount of blood ejected from the ventricles during systole, one heartbeat is 70 milliliters of blood, and that is called the stroke volume. So think of each beat as a stroke. So the stroke volume, 70 mils. What is remaining after ventricular systole, so after ejection, is called the end systolic volume. And so that's going to be about 60 mils. So the volume remaining in the ventricles after systole. So what I'm saying is when the heart contracts, so the ventricles contract and eject the blood out of the heart, there's still some blood in there. It's never like the heart is ever dry. So we have ventricular ejection phase. And then at the beginning of ventricular diastole, so early diastole, look here. Remember, this heart's going to relax and it's going to slam those semilunar valves closed. So we have this little brief moment in time here that's called iso, means equal. So think of isosceles triangle. Isovolumetric relaxation. And so the heart's just going to relax. At this point in time, there's not enough pressure for these AV valves to open yet. Once the atria fill up enough and the pressure is great enough, then those AV valves open and then we just start our passive filling again. Don't forget that dub sound. That's those semilunar valves slamming shut. So second heart sound. If you notice, feel your own heartbeat. That second heart sound, it's louder. And that's due to that higher back pressure in the systemic circuit. Kind of think of just slamming a door really, really hard. And so that sound is going to be louder. This diastole, so phase 3, early diastole, and I said we had ventricular filling. What this is doing is it's conserving the energy of the heart. So the heart actually at rest, normally it's going to work about 40% of the time, and it's going to rest about 60% of the time. And I'm not saying your heart's lazy, because it certainly isn't, but it has to conserve energy. We need the heart to relax, so both the atria and the ventricles, they relax at the same time to allow for that adequate blood delivery to the myocardium. So recapping, we have passive filling during rest. The atria are going to contract first, so atrial systole tops off the volume in the ventricles. So then we have end diastolic volume, about 130 milliliters. Then the atria relax, and then it's time for the ventricles to contract. So then we get ventricular systole, which is ventricular ejection. They're the ones that are actually responsible for blood leaving the heart. So moving heart through the pulmonary circuit from the right side and moving blood to the body through the systemic circuit on the left. So ventricular ejection phase, and then they both rest. So atria contract, relax, ventricles contract, relax, and then they both rest for a time. And so like I said, this conserves the energy of the heart for about 4 weeks in utero, 20 days gestation. A baby's heart will beat, and then it beats throughout the course of a person's lifetime until the day that they die. So the heart it deserves that little 60% rest. This is a big messy diagram. I realize that. So pop down here, we're just going to take it in pieces. So we kind of walked through this, and I just want to, so you don't get lost in the math, and I've even adjusted the math for this particular textbook. We're going to go with my math. How about that? But remember, we've got the ventricles passively filling, and then the atria contract. So the max after the atrial contraction is called the end diastolic volume. When the ventricles contract, they're ejecting blood. So what is left after ejection, so after systole, is the end systolic volume, which is about 60 mils. So if you take your end diastolic volume and subtract it by your end systolic volume, that's how you get your stroke volume. And they just give the lab average for 70 mils, and that's the amount ejected per heartbeat by both sides. So 70 mils goes to the lungs, 70 mils goes to the body. We're going to connect that later, but this is showing you the heart sounds though. So remember, the heart sounds are the closing of the valves. First heart sound, atrioventricular valves. Second heart sound, the semilunar valves. So, yeah, everything I just said. Pause. The pause where you hear nothing, that's when your heart is relaxing. The term heart murmur. So heart murmur means any abnormal heart sounds. And we listened to some of them already. Usually they're going to indicate an incompetent or a stenotic valve. So either a leaky valve or a stiff valve. Like I said, when blood leaves and moves through the heart smoothly, without that backing up of blood, then normally you just hear really crisp heartbeat sounds. And so we listened to some of those already. Where you place the stethoscope, some of you may be clinicians already, some of you may have at least been to the doctor, I hope, and you know the clinician is always going to just kind of listen to your heart, and they kind of move that stethoscope around. What they're doing is they're placing the stethoscope in the optimum location that they can hear the closing of those valves. And so, remember, we have the heart sitting in the chest. The base is about that second rib. So you want to listen for the semilunar valves in that second intercostal space. The thing that's weird, because the heart is not sitting symmetrically, you know, like we draw it like a Valentine heart, it's kind of turned on its side, it's pointing over here to the left hip. And so to hear the aortic valve, you actually would place the stethoscope to the right of the sternum. So just to the right of the sternal margin in that second intercostal space is the ideal place to listen to the aortic valve. The pulmonary semilunar valve, you'd want to hear that on the left side. And I know that sounds weird. I just remembered it anatomy physiology, so AP. Sorry, don't have anything better. It's just the way the heart is turned, and just to listen for the closing of that particular valve, that's where you would place the stethoscope. And so if you heard a murmur over here, you would know it was the aortic valve. If you hear a murmur over here in that second heart sound, remember that would be the pulmonary valve. Down here, it kind of makes more sense. So the tricuspid valve is going to be on the right in that fifth intercostal space. And to hear the mitral valve close, you would go mid-clavicular line in that fifth intercostal space. And that would be where you would listen for the closing of that mitral valve. And once again, these are atrioventricular valves. So you're going to listen in that first heart sound. That's what you'd be listening for, a nice crisp closure. If you hear a murmur, then you would know which valve was incompetent or leaky. So let's just do a little bit of a review about cardiac muscle. I know you studied it in AP1, but you've probably shoved a whole bunch of other stuff in your head since then, so I always kind of like to do a little review. So cardiac muscle, the contraction is going to involve, we're going to talk about 3 ions. So sodium, potassium, and calcium. Remember, so you want to pop down here with me. Cardiac muscle, they were striated like skeletal. They were unicellular. Sorry, they were 1 nucleus per cell, so uninuclear, and they were branched. They were connected through these intercalating discs. So that was kind of your tell if you had a tissue lab practical. That's how you could tell. They have desmosomes, which these are these tight junctions that are basically going to help the heart muscle hold together, so give it integrity so it doesn't separate. But the big thing that they have is gap junctions, and that's exactly what that sounds like. These are gaps for ion movement. And so that just allows these cells to be electrically coupled together. What I'm about to tell you is that your heart and this beat has to be very coordinated, and either your heart beats as a unit or it doesn't. And that term for beating as a unit is functional syncytium. So your heart either beats or it doesn't. So it doesn't kind of sort of beat. So either you're going to have a heartbeat or you won't because of these connections. So we're going to look at some differences between cardiac muscle and compare it back to skeletal muscle, because you probably spent a lot of time on skeletal muscle. So number 1% of the cardiomyocytes have what's called automaticity or autorhythmicity. They do not need nervous system stimulation to initiate muscle contraction. Since all of these cells are connected, these cells can depolarize and initiate an entire heartbeat without a motor neuron, without any stimulus from the autonomic nervous system. So remember, your skeletal muscles, they only contract when you tell them to, not so with heart muscle, and we'll look at why in just a little bit. All the cardiomyocytes, like I said, they contract as a unit, or none of them contract. Whereas remember, skeletal muscles, they have motor units. So there are large motor units, which would give you a big, powerful contraction, or small motor units, which would give you fine, delicate amount of force generated. So that's not the case with cardiac muscle. Just looking down here structurally, and I don't really care that you know that whole lot, but we don't have those terminal cisternae and things like that. But we still have some T tubules. We got the sarcoplasmic reticulum still involved, and it's going to warehouse our calcium for us. We still have sarcomeres. We have overlapping. We've got the thick filaments, the myosin, and the thin actin heads. And so each sarcomere, remember, shortens. And so we're going to get contractions of these muscles. They are in that spiral pattern. And so our goal is going to be to move blood, so for blood ejection. Other things, which is muy importante. Cardiac muscles has a longer absolute refractory period. We're still talking milliseconds, but what their ion channels, what they are going to do is they're going to go into an inactivated state. And so that means when they're in an inactivated state, no matter what happens, that gate is not going to open. Think about it. You've all had muscle cramps in your skeletal muscles at some time in your life. What we don't want, the heart can't have a cramp. Okay? That means just sort of think about it. We can't have that tetanic contractions. We can't have maximum muscle contraction of the heart where it just stays there. And so that's the purpose of that longer absolute refractory period. The other thing that's different is that, remember, calcium was a switch for excitation contraction coupling. So remember, we have our troponin and tropomyosin. Those were our regulatory proteins, and they blocked the binding site on actin, so those myosin heads couldn't attach and shorten. So as long as there was calcium out here in the sarcoplasm, then we got muscle shortening. So calcium's still going to be locked up in the sarcoplasmic reticulum, but some of that calcium is also going to come in externally. And so that's a little bit different. And so we're going to get a different action potential, which I'm going to show you. But about 20% of the calcium is going to come extracellularly. The rest of it's going to come from that sarcoplasmic reticulum. We're going to get a plateau phase, which you won't see in skeletal muscle because we have this external calcium. The point, we want to allow time for blood to be ejected. Just hang with me. Okay, so this picture, I'm gonna, hopefully, like I said, you kind of remember skeletal muscle. So this is showing resting membrane potential. And remember, there's two parts to an action potential. You got depolarization and repolarization. So sodium moved in and then potassium moved out. And this purple and green represent the refractory period. And we know that once we had an action potential, we got muscle shortening. So we got muscle tension, so it contracted and then it relaxed. Cardiac muscle is a little more complicated. So we're going to have 3 phases. And notice we have a long, drawn-out contraction compared to skeletal muscle. And then 2, I also want you to see that we have a much longer refractory period because we don't want that continuous action potential. If you guys kind of remember skeletal muscle, you could receive another action potential, and that's how you got up to wave summation, up to tetany. If you don't know what I'm talking about, sorry, you're going to have to go back and check that out in your textbook. So I gave you this picture. I'm going to teach it to you using another picture. Well, several pictures. Okay, so we're going to walk through the action potential of a cardiomyocyte. And so just before we begin, I kind of want to remind you where the ions are. So normally, because of the sodium-potassium pump, we have a concentration gradient outside of cells. So there's way more sodium outside of the cell compared to inside of the cell. Potassium, remember, the majority of potassium is going to be inside of a cell compared to outside of the cell. Calcium, you probably didn't talk about a whole lot, but I'm going to tell you. There's very little extracellular calcium. The majority of calcium is going to be inside of the cell, locked up in the sarcoplasmic reticulum. But there is more calcium outside of a cell compared to inside in the cytoplasm. Okay? So we have these concentration gradients. Ions typically cannot move through that phospholipid bilayer because ions are charged, and then we've got a fatty bilayer. So they're going to enter and exit through gates, so through ion channels. And so I just kind of, this is where we're starting. There's more sodium and calcium outside and more potassium inside. So all we have to do is, if there's a gate that opens, these ions are going to move based on their concentration gradient from greater concentration to lesser concentration. So you've probably seen these if you work in a hospital or you watch any sort of medical show. So boop, boop. You've seen this shape before. Okay, so we're going to look at the 3 phases. So this is resting membrane potential. So this first phase right here. So we are going to go from about -90 to about 30 millivolts. And so this is going to be called depolarization because we were polarized and now we're not polarized. It is due to sodium influx. So we have fast voltage gated sodium channels are going to open and sodium is going to rush in. So positive ions rush in, this becomes more positive. When we get up here, those sodium gates are going to close. And then we're going to have our next phase, which is called the plateau phase. Remember plateaus, the flat parts of, rocks, like a mountain with the top cut off. So plateau. So the sodium gates closed, and now we're going to have slow calcium gates open. So now we've got calcium coming in, but we also have some potassium channels open, so potassium is going out. So the amount of calcium coming in is going to be equal to the amount of potassium going out. And so this is going to drag out that plateau phase. And also this is what's sort of increasing our absolute refractory period to prevent that heart from cramping. And so we get this tension in the heart muscle. And so that plateau phase is going to last as long and kind of give us time to get up to that tension. So we get tension. The next phase is called repolarization. So depolarization, we lost our polarization. Flat part was the plateau phase. And now we are repolarizing. So the calcium gates are going to close, and now the potassium gates are going to open. And since we had more potassium in than out, potassium is going to move out of the cell. So now we're going to lose positive charges. So now we go back down to our resting membrane potential. And then we have the sodium potassium pumps that are going to put the sodium potassium back, and then there's calcium pumps that are going to put the calcium back. And so then it's going to be restored, and then we can do it all over again. All right, so this, I love colored pictures. So once again, we have depolarization because of those fast sodium gates. Sodium channels close. We have slow calcium channels. So we have calcium moving in, but we have some potassium leaking out. Then those calcium channels close. We get repolarization because potassium channels open and potassium goes out. So what I want you to see, so this whole time we have this action potential, it is refractory. And don't worry about absolute and relative, I don't care, but I want you to see it has a very long extended refractory period. So refractory period in cardiac muscle lasts as long as ventricular systole, which is good. If the ventricles are ejecting blood, we don't want another action potential or contraction initiated. We need to have contraction, so systole, and then we need it to relax. We need ventricular diastole. So the big thing prevents tetany, ensures the heart doesn't cramp. Hopefully that makes sense to you. The reason why we had to talk about all that, and I sort of plagued you with all those ions, one, you do need to understand that. But the big thing when you go to pharmacology, there's a whole class of drugs called calcium channel blockers. So we talked about calcium channels in the heart, which are responsible for that plateau phase. If we block some of those, that's going to drag out that plateau phase. It's going to decrease the heart rate. It's also going to decrease blood pressure. So it kind of saves the heart and lowers blood pressure. Okay, I'm going to stop this one here, so if you just want to watch that part again, you can. Come back for our last installment. Have a great day.